Okay, let's continue the discussion. Okay, so far no, we are familiarized na no, we have been introduced dun sa architecture ng ORAN, no. Ngayon naman no, let's see how the ORAN architecture no complements with 3GPP and other industry standards. Okay, so again, no, ito na naman yung itsura no, ng ating core and access networks. And then basically yung ating access network no is functions no like this. No? Ito po yung kanyang mga ginagawa. No? The functionality of ORAN or of RAN itself no, is on the first three layers of the OSI model. So from the physical layer, the data link layer, and the network layer. Okay, so if we look at that, if you look at the components, now the RRU and the BBU, the RRU is in charge of the radio frequency na RAN protocol. This is considered the low-fi or parang low na physical layer. And then the other functions of the physical layer, the hi-fi, is assigned no, dun sa BBU or the baseband unit. No? All the upper protocols, so from the data link layer protocols at saka network layer protocols, those are handled by the baseband unit. No? So ito mga to, no? The Service Data Adaptation Protocol, SDAP, Radio Resource Control, RRC, Packet Data Convergence Protocol, PDCP, Radio Link Control, RLC, and Medium Access Control, MAC or MAC. No? Okay, so it's understandable na at first that all these protocols are new, no? So it's okay if hindi siya agad-agad maintindihan or ma-memorize. So but this is the different functions, no, or different protocols that lie on the OSI model na ng ating radio access network. No? So you can see here yung SDAP, no, this is for handling of the quality of service. RRC is for connection management and mobility functions. Yung PDCP is for IP header compression. RLC is for segmentation of the PDUs. No? At saka yung automatic retransmission request, no? Error correction. No? Medium access control for multiplexing. Then yung hi-fi, no? High physical layer, which is just the physical layer in the RAN. This one is for modulation, demodulation, saka yung CRC error correction. And finally, yung nasa RRU lang no, is the radio frequency or the one converting the analog to digital and from the digital to analog as well. Okay, so actually all of these different protocols in the radio access networks, all of them are specified in 3GPP. So if you search in 3GPP, may mga technical specifications doon, may TS and then the number itself. Then each of them will have a separate document specifying each part, specifying the RAN protocol. And also depending on the generation, pag UMTS, di ba, node B, yung kanyang node name, no? And then for 4G LTE, it's E node B. And for 5G new radio, it's G node B. So magkakaiba po silang specifications. But you can see yung first number, pag 25, that is for 3G. Ito naman 36, no? This is for 4G. Then 38, saka yung 37 is for 5G. So notice as well that the SDAP is only applicable to the 5G. No? It was not yet specified during the 3G and 4G specifications. No? But for the others, meron pong parang mga updated sila, no? Specifications depending on the type of generation. No? Okay, so if you search na these different specifications, may mga titles pa yan, no? Kung ano po yung particular specification na yun. No? And eventually, no, may mga versions pa sila, no? Kung ano yung versions na applicable today, no? Kasi each of the technical specifications na update siya din no? From time to time. And eventually, pag nagkaroon na rin ng 6G, no? Magkakaroon na rin ng separate na specifications for them. No? Okay? So itong lahat ng ito, no, all of these three, no, are radio access network protocols. No? This is dun sa part ng RRU at saka ng BBU. Okay, so we have seen that each of the components of the BBU, no, DU and CU will have a certain protocol, no? Certain protocol to be implemented. So ito yung mga protocols earlier. You have the RF, low-fi, hi-fi, meron pa further, no, the low MAC, high MAC, low RLC, high RLC, PDCP, and RRC. So ito yung from the first, no, lowest layer papunta sa highest layer dito sa kanan. No? So the data is coming from the upper layers, of course, going down to the network layer. No? So dito na po papasok. No? Here is where the functional split options comes into play. So since in OpenRAN, the distributed unit and the centralized unit are separate functions of the baseband unit, it depends on the mobile network operators, which particular protocol of the RAN will be assigned to the DU or will be assigned to the CU. I mentioned earlier there was the high layer split, no, at saka low layer split. If we have a low layer split, we are specifying, no, kung ano yung protocol running on the radio unit, saka ano yung mga protocols running on the distributed units. So, for example, here, no, if you choose, if the mobile network operator chooses option 8, that means the RU is in charge only of the RF protocol, and the upper parts will be in charge, will be managed by the other component, yung DU natin. On the other hand, if they choose to implement option 7, that means the radio unit will be in charge of the low-fi and the RF. So, di ba, yung low-fi kanina, that one is in charge of the modulation, demodulation, and CRC error correction. No? So that means these two functions, so these two protocols will be assigned to the remote radio unit. No? That is what the functional split means. No? Whatever the protocols, no, will be assigned to a particular component. No? If we consider higher layers or high layer split, then you're just defining what are the different protocols assigned to the CU or the centralized unit and to the DU. So if you choose option 1, that means the RRC, this is assigned to CU, and all the others will be assigned to the DU. Okay, so actually more discussion po on the different functional splits in the next lecture. But to give you an overall idea on what functional split means, we're just defining what are the functions, what are the protocols assigned to each component in the OpenRAN architecture. What is assigned to the radio unit, what is assigned to the distributed unit, and what is assigned to the centralized unit. Okay, so the mobile network operators can choose whatever kind of option that is more feasible in their implementations. So itong slide na to, this slide is taken from parallel wireless. Okay, so aside from the 3GPP specifications and the OSI model, let's look at the different functions and nodes in 3GPP and ORAN. Okay, so we are already familiar that we have the core network, and then the core network connects to the baseband unit through the backhaul or the transport network. And then the baseband unit is composed of the CU and the DU. Again, the CU is the centralized unit, the DU is the distributed unit. And then based on 3GPP, when we started to split the BBU, we now have the CU and DU that is connected by the mid-haul interface. The mid-haul interface natin is F1. This is defined by 3GPP. And then the front-haul interface is the interface between DU and RU. Okay, so this is the 3GPP architecture. And then for the ORAN overall architecture, we now have this. So it's quite similar because you still have the RU, DU, CU, but in this case, the CU is now separated into two. One is for the control plane, the other one is for the user plane, and then the E1 interface connects the two. Okay, and then also we have the near real-time RAN intelligent controller or RIC, and also the SMO, no, system management and orchestration. This is the same overall architecture that I have shown earlier as well. As we have also seen, no, in the previous slide, in the functional split, no, basically the RRU will just be in charge of the lower part, no, of the physical layer or the whole physical layer, and then the baseband unit, no, this part here or the distributed unit, no, is in charge of the processing, the MAC, no, and the CU is in charge of the upper network layer protocols. Okay, so there are four functional components here. We have the distributed unit, the ODU. The O is just OpenRAN or basically ORAN or open. So the DU is the distributed unit here. Then the multi-RAT CU is this two. So when we say multi-RAT, is a multiple radio access technology. No? It is able to utilize the different cellular networks. So not only just 5G, it can also handle like 4G. No? Then we have the near real-time RIC. Again, when we say near real-time, it is in charge of the tasks that are less than 1 second of latency. And also in the near real-time RIC, that is where the X apps are. No? So this is the question earlier in the Kahoot. No? Nauna yung question na before the discussion on X apps. No? Okay, so X apps are in the near real-time RIC. Tapos meron pang tinatawag na R apps. Yun po ay nasa non-real-time RIC. No? So mas madidiscuss pa po yan in the next lecture as well. No? Just keep in mind X apps in near real-time RIC, R apps in the non-real-time RIC. Okay, so also another function here, another functional element is the SMO. So ito po ating SMO sa taas. It also has the non-real-time RIC as we have seen in the ORAN architecture earlier. The non-real-time RIC handles tasks that are greater than 1 second na latency. Okay, so all of those, so for example, management for, or rather for analytics, so data analytics, mga model training for machine learning, all of them will be handled by the non-real-time RIC because all those applications, all those tasks require more than 1 second to be before it is completed. Okay, so each of the functional software elements is deployed as a virtual network functions, small letter S, or containers to distribute capacity across multiple network elements with security isolation and scalable resource isolation. Because of virtualization, the functions of the software or the different components are now virtualized or now in containers. We can simply just have a virtual machine assigned to perform this task, assigned to perform that task. They can be proprietary, but as long as the hardware, the server handling these functions are open, then that is OpenRAN. Okay, so also we have the two RIC here, the RAN intelligent controllers. This RAN intelligent controllers can help optimize the whole network here. Okay, so ayan, I've mentioned earlier the RAN intelligent controllers. In earlier generations, there are actually controllers, but they have a different name, somehow different name. So controllers for 2G and 3G, there are specified controllers like the BSC, base station controller, and RNC, radio network controller. They were responsible for RAN orchestration and management. But starting 4G, when we now have the Evolve UTRAN or yung meron ng eNode B, there is no separate controller element to simplify the architecture and allow faster response times. So there is just an optional interface called X2, that is in charge to allow exchange of information between eNode Bs. No? Ang naging challenge here, however, is that the X2 interface to allow the communication between eNode Bs is proprietary because each vendor had their own version of the X2 interface. So by the time that 5G came, there is now a RAN intelligent controller, and then the RAN intelligent controller enables the uh, eNode B and gNode B functionalities for intelligence, resource assurance, and resource control. So that because of the virtualization and software-defined networking, no, you're able to allow configuration ng mga different infrastructure or different software, no, ng radio access networks. No. Okay, so yung RIC, no, yung RAN Intelligent Controller, started in 5G. No. Although earlier there were some controllers, no, but they are different, no, from the RAN Intelligent Controller that was created in 5G. Okay, so the RAN Intelligent Controller, no, it was started, or it was defined because of the need for 5G applications to have low latency. 5G specifications require network functions, no, to be virtualized, or dapat ata VNF, no, virtualized network functions, and SDN, no, software-defined networking, to enable configuration, optimization, and control of RAN infrastructure at the ends. No. So RIC enables the functionalities for different functions, no, for different purposes, no, for intelligence, no, and control. No. It is originally defined for 5G Open RAN, but eventually, no, it can be employed as well, no, for 4G and 2G and 3G. Pero there is, of course, parang separate function, no, para to allow the operation to be implemented in the other versions, other generations. No? So the RIC allows the interoperability of different hardware and different software components. And because it can handle the data analytics, it can acquire the data. No? This allows us to apply machine learning and artificial intelligence for better resource management. No? So for the purpose of optimizing the applications, like for example, the quality of service, mobility management, and mga interference management, etc. No? Okay, so the RIC, no, allows a self-optimization of the radio access network, no, for the purpose of efficiency and handling the RAN task. No. Okay, so we know that there are two different RIC, no, inside the overall architecture. We have the non-real-time RIC, no, and the near real-time RIC. No. Okay, so pag non-real-time RIC, that is located at the SMO part, no? And the near real-time RIC, no, is one that is connected to the SMO and to the OCU, no, saka yung ODU. No? Okay, so for non-real-time, from the word itself, no, it is for the task that require greater than 1 second latency. No? So it takes longer than 1 second to complete. But for near real time, usually these are tasks that require less than 1 second of latency. Okay, so specifically yung mga tasks, no, that require greater than 1 second latency are apps. No? They can be used for RAN automation, optimization, pwede for analytics. No? For example, if they have third-party application to provide value-added services, maybe for traffic forecasting, no, traffic congestion prediction, no? Basically anything that requires additional intelligence. No? Those are our apps, and they can be deployed, no, in the non-real-time RIC. X apps, on the other hand, X apps are in the near real-time RIC. These are services, no, or microservices that can be used for radio resource management. Okay, so These are for E Node B and G Node B functionalities. For example, scheduling, radio resource management, basically. Okay, so if you hear non-real time, that one is for our apps. Near real time is X apps. No? There are several companies that deploy their own versions, no, of X apps and R apps. No? If you search, no, X app, and then they, like, I think Ericsson also has one. No? They have their own software, no, in X app nila, to be deployed in a near real time RIC framework. No? Okay. So now let's proceed dun sa different interfaces that we have heard earlier in the architecture, and basically all of the interfaces in ORAN is open. Okay, so this is another way of viewing the overall network of the telco. We have here the core network sa left, sa right, no. Then the core network connects to the radio access network via the backhaul, which can be a fiber optic, microwave link, satellite microwave link. And then the BBU here is the one handling most of the functions of the radio access network from the high physical layer, MAC, RLC, PDCP, and RRCP. And then the BBU connects to the RRU via the front hall interface, and this RRU is in charge of managing the RF component or the RF functions. Okay, so in 4G RAN, no, the hardware for 4G RAN is called the E Node B, and in 5G RAN, the hardware is called the G Node B. Then of course we have the RRU connected to the antenna, and then the antenna will be the one that is the air interface towards the user equipment for uplink and downlink connections. Okay, so now we have a front hall and back hall, and in OpenRAN, the DBU is split into the DU and the CU, and we now have the mid-hall interface. Okay, so this is front hall, mid-hall, and back hall. So FH, MH, and BH. We have the mid-hall because of the disaggregation of the BBU components. Okay, what else? Also in the 3GPP interfaces in 4G LTE, there is now also S1 interface. The S1 interface is the interface from the RAN to the core. And then we have the UU interface. This is the air interface from the basically from the access network towards the user equipment. Okay, so this is just a simplified 4G LTE mobile network architecture. And these are two 3GPP standardized interfaces from a RAN point of view. Okay, and then the 3GPP interfaces inside the RAN, we have the front hall interface connecting the node to the remote radio head or remote radio unit. And then the X2 interface connects the E node Bs. Earlier I mentioned this. This X2 interface allows the different nodes in 4G RAN to talk to each other. But the challenge here is that the X2 interface is often proprietary. The X2 interface is dependent on the implementation of the vendors. Okay, so also yung front hall interface natin here, the one connecting the baseband unit to the remote radio head, that one traditionally is using CPRI protocol, which has been generally a vendor-specific implementation. Okay, so in OpenRAN, there are other open front hall alternatives like the CPRI, defined by ORAN, FAPI and NFAPI defined by the Small Cell Forum, and other Ethernet-based front hall options. So it was very important that the front hall interface is open, since otherwise, if it is proprietary, that means the hardware that you will buy should be able to should be compatible to the interface. So if the front hole interface are not open, then the operators are forced to deploy vendor-locked upgrades of their RRU and DBU. Okay, so let's look at the different front hole interfaces. Now, one is the CPRI. So in the CPRI, this is an earlier version, no, in 2015. This connects the radio equipment or the RU to the BBU. In CPRI, we call the RU as the radio equipment, and in BBU, that's the radio equipment control. EC3 is the one that is now open. It's not necessarily vendor based, no. And if you have ECP, you have an enhanced radio equipment and an enhanced radio equipment control. Okay, so there are other use cases, no, for ECP using 802.3. Okay, so this is the front hole interface. No. One is proprietary and the other one is open. Okay, so other options for the front hole interface is the FAPI, or the Functional Application Platform Interface, or FAPI. It's a common standard agreed between chipset and component suppliers and mobile base station integrators. It is an API for hardware components implementing the 3GPP physical layer functions. So it allows mixing of SDUs, no, small distributed units and small centralized units. So since this is mostly for small cells, the mga picocells, you know. Okay, so the network FAPI or NFAPI is the interface between the DU and RU of a split 5G RAN small cell network. This particular front hole interface is specified under the RAN functional split 6. If you go back to the functional splits, we have seen that there are functions, there are protocols that are assigned for the RU, DU, and CU. Okay, so the small cells, of course, are those are often usually the in-building solutions. Okay. Then this one is also another interface that is open, but less used, no, mas commonly used yung NFAPI and FAPI, no, saka ECP. This one is radio over Ethernet, no, ROE. So it is defined by IEEE 1914.3. So this one just explains how to connect, no, the ROE via CPRI or other interfaces. Okay, and then another interface in OpenRAN, or in RAN, no, you have the X2 interface. This was the connection between the eNode Bs in the 4G network. It supports the exchange of information between eNode Bs, and it is an optional interface in 4G networks, but it is essential, no, in seamless multi-vendor and multi-network RAN deployment. Okay, so this interface performs the following. We have the handover, the load management, the inter-cell interference coordination, the network optimization, etc. So this was the X2 interface. It started, no, as an optional interface in 4G, but later, no, it allows as well, no, multi-network RAN deployments, no, for 4G and 5G as well. Okay, so now let's look at the 3GPP interfaces in 5G NAN standalone, or NSA. So in 5G NSA, the 5G RAN relies on core 4G network, while existing 4G RAN continues to operate. So for example, here, no, we have the eNode Bs, and then the S1, this S1 here connects the eNode B to the core network. Then the front hole interface, or FH, connects the eNode B to the RRH. Okay, so yung X2 is the one connecting the eNode B and the eNode Bs, no, of the 4G network. No? And the NSA, of course, is just the is based on 4G. so that to allow transition from 4G to 5G. Okay, so if the X2 interfaces are not open, that means the operators may be forced to deploy vendor locked upgrades of their BBUs. Okay, so in summary, these are the different interfaces that are in the architecture. We have the user equipment. This is the air interface, or sometimes called the EU interface. Then we have the radio access networks or radio access network. That one is the one between the CN, the core network, and the user equipment. And then inside the RAN, we have the antenna, the RRU, and the BBU. Okay, so the BBU itself is composed of the distributed unit and the centralized unit. So DU and CU. Connecting the BBU and RRU, or remote radio unit, is the front-haul interface, FH. This can be CPRI, eCPRI, FAPI, and FAPI. More on that, more on which particular interface is used depending on the split option. More on that in the next lecture. And then for BBU, we have DU and CU, the distributed unit and the centralized unit. It was split by 3GPP. There was a technical report, technical report 38.801. It showed the split architecture of the BBU, and then the two components are connected by the mid-haul interface. Okay, and then connecting connecting different nodes, node Ds in 4G, we have the X2 interface. So this was created because there was no controller in 4G. So the different nodes are just talking to each other using the X2 interface, which was originally, it is not open because each vendor had their own version of the X2 interface. Okay, what else? Of course, the backhaul. The backhaul is the one connecting the core network to the BBU via the centralized unit. This is the S1 interface. Okay. And then also some ORAN interfaces. We have here, again, the overview, the architecture. We have the SMO, the near real-time RIC, the centralized unit control plane, centralized unit user plane, and then the distributed unit and radio unit. Remember, the O here just means ORAN or open. So this is open distributed unit and open radio unit. Okay, so what are the interfaces here? We have the open front-haul interface. This is the connection or the interface between the radio unit and distributed unit. Then we have the mid-haul interface here between the DU and the CU. So that is the F1 interface. This is an open interface defined by 3GPP. Then also another interface is the E2 interface. This one connects the real-time intelligent controller, or sorry, the near real-time RAN intelligent controller connecting to the CU and also the DU. So you can see there is a line here, of course. And then the E1 interface is the one connecting the CP and the control plane and the user plane of the centralized unit. Then the A1 interface is the near real-time RIC interface to the SMO. Okay, so this is the last part of this lecture. We'll hopefully finish in just a few minutes since the next speaker has already arrived. So just some implementation options and deployment scenarios. So in the traditional deployment scenario of RAN, we have the RAN software and then the RAN hardware. The RAN hardware and RAN software are all proprietary. So if ever you need to change one component, if you need to change a hardware, it must be compliant. It must be interoperable with the other hardware. The same goes to the software and platforms. They should be compatible to the proprietary hardware. But for OpenRAN deployment, no, it is now running, no, on top of open hardware. No? The hardware can be coming from different vendors. No? Like for example here, vendor ABC, no? And then these are commercial off-the-shelf servers. Okay, and then the software running on top of the servers, the commercial off-the-shelf servers are open as well, or OpenRAN software as well. Okay, so the service provider or mobile network operator can replace the OpenRAN hardware and software easily if they prefer to use a different hardware, or if the hardware goes down or is no longer operating, they can immediately buy or purchase from another vendor if they want. No? And then due to open interfaces, hardware from any vendor can be swapped and should still work for the software from other vendors. No? Even with new software from vendor 2, the existing hardware should still work. Okay, so same concept. In 5G Open RAN, you'll have the commercial off-the-shelf servers as well. And you may have different vendors, no, for each software, no, and then also different hardware implementation. So this is it is allowed interoperability between the hardware and software of various vendors, no, due to open interfaces. Okay, so in parallel wireless, no, they provide some solutions, no, to allow the operators and vendors to move towards supporting 5G or all G Open RAN solutions. Right. So this is just their overview, no, of their implementation. No. They can provide all G solutions. That means 2G, 3G, 4G, 5G access. And they also have some software implementations, no, of the different virtualized network functions. Okay, so ayan, so saktong-sakto. Summary of this today's lecture. We have learned that the radio access network RAN consists of the radio and baseband units, the RU and DBU. The radio access network name differs depending on the considered cellular generation, whether it's GSM Edge RAN, Universal Terrestrial RAN, Evolved or Enhanced Youth RAN, and 5G RAN. This RAN architecture evolution happened with the disaggregation of the hardware and software components, brought about by the virtualization and software-defined networking. In traditional and centralized architectures, hardware and software are often proprietary. And then in the virtualized RAN, on the other hand, it still includes proprietary hardware interface and software running on the COT server. In Open RAN, all components, including the interfaces, should be open. All the hardware is open. In Open RAN, there are 4 main functional components. We have the DU, distributed unit, centralized unit, and the near real-time RIC, and the SMO with the non-real-time RIC. Remember, if we have a near real-time RIC, they are the ones in charge of tasks that support less than 1 second of latency, like yung mga X apps. And the non-real-time RIC is in charge of the tasks that support greater than 1 second of latency, kagaya ng mga R apps. Okay, there were also several interfaces that we have covered, like for example, the air interface, the front haul interface, mid haul interface, and back haul interfaces. Okay, there are also other interfaces, all of this, A1, E1, E2, F1, O1, O2, S1, X2, all of them were presented in the ORAN Alliance reference architecture. So the one with all the components and the interfaces. Okay, so that is all for this particular lecture. You can view or read more about this in the following readings or in the following videos as well. Okay, thank you for listening.